In this video, we're going to investigate percent reaction. So percent reaction is how we determine the extent to which a reaction occurs in an equilibrium system. First, we need to understand quantitative versus equilibrium reactions. So a quantitative reaction is kind of what we had studied up until this point. And a quantitative reaction means that 100% of the limiting reagent is consumed or used up, and we produce the maximum amount of product possible. So if we imagine a reaction, A to B, and we start with 1.0 moles of A, we should have 1.0 moles of B after the reaction, because we'll have used up all of A and converted it to B. In an equilibrium system, less than 100% of the limiting reagent is consumed. So we always have some product and some reactant present in an equilibrium system. This means that less than the maximum amount of product is produced. If we had the same reaction, so A to B, and we had 1 mole of A, we would produce less than 1 mole of B. Now that value could be 0.01 moles of B, it could be 0.99 moles of B, but it will not be 100% of what we could produce. We're going to go through two examples to really understand percent reaction. So in our first example, 2.0 moles per liter dinitrogen tetroxide decomposes to nitrogen dioxide to form the following equilibrium. So in our equilibrium, we have 1 mole of dinitrogen tetroxide decomposing into 2 moles of nitrogen dioxide. At equilibrium, the concentration of nitrogen dioxide is 2.75 moles per liter. So we're going to find the percent reaction. The way that we're going to do this is using an ice table. And I'm going to draw two ice tables just for our comparison. One where we have a quantitative reaction and one where we have equilibrium. So I'll draw our quantitative ice table over to the left here. So dinitrogen tetroxide produces 2 nitrogen dioxide molecules, initial change, and then I'm going to call this final instead of equilibrium. So we know that initially we have 2.0 moles per liter of dinitrogen tetroxide and 0 moles per liter of nitrogen dioxide. In stoichiometry to date, we've worked in moles instead of concentration. However, we can use mole ratios to predict the amount of product that we're going to form because they're in the same vessel. So we don't have to convert to moles because they're in the same container and the volume is the same. So if all of our reactant were used up, so our reactant is dinitrogen tetroxide, the change here would be -2, leaving us with 0 reactant. If our change for our dinitrogen tetroxide was 2, -2, it must be +4 for nitrogen dioxide because we have 2 nitrogen dioxides for every 1 dinitrogen tetroxide. So this is going to be +4. So our final concentration in this case would be 4. This is the maximum concentration possible for NO2 if all of the dinitrogen tetroxide reacted. We are going to do an ice table again, this time for our actual equilibrium concentration. You may not have to do this ice table, but it's good practice to kind of keep using this tool so that you get really comfortable with it as you're going through your chemistry practice. So initially in this scenario, we had 2, and we know that our equilibrium concentration here is 2.75. So this is a change of +2.75, and this would be a change of half of that. Half of 2.75 is 1.375, and 2 minus that is 0.625. So we can see at equilibrium that we're going to have some reactant and some product left. And so this value, this 2.75, is our equilibrium concentration. And so to find our percent yield, we are going to use these two numbers. So our percent yield is going to be our equilibrium concentration of NO2, so from the ice table on the right, divided by the concentration of NO2 we would get in a quantitative reaction, which is the ice table on the left, times 100%. So 2.75 moles per liter divided by 4 moles per liter times 100%, and we get 69% reaction with our sig digs. A percent yield like this indicates this is a product-favored reaction or product-favored equilibrium because our yield is over 50%. In our second example, we have 2.0 moles per liter nitrogen and hydrogen gas is introduced into an empty flask. The following equilibrium is established. So we have 1 mole of nitrogen plus 3 moles of hydrogen in equilibrium with 2 moles of ammonia. At equilibrium, the concentration of ammonia gas is 0.25 moles per liter. Find the percent reaction. So once again, I'm going to set up our two ice tables. So N2 plus 3H2 forms 2NH3. We'll have ICF. So we have 2.0 moles per liter of both of these and 0 of NH3. Now this is an LR-ER problem. So I'm actually going to set up a second quantitative ice table just to compare. There's lots of different ways you can do the LR-ER math here, but I'm just going to keep using our ice tables so that we're practicing that skill. So if nitrogen is our limiting reagent, the change in nitrogen would be -2 if it was all consumed, which means our change in hydrogen would be -6, and our change in ammonia would be +4 because of our relative mole ratios. So 2 times 3 is 6, 2 times 2 is 4. There's a big issue with this in that we can't have 2 minus 6. That will not work. And so what that tells us is that N2 is our excess reagent, and so we're not going to use it to determine our yield. So we're going to use the second ice table I've set up, this time using hydrogen as our limiting reagent. So if we consume all of our hydrogen, the change for nitrogen will be 2 divided by 3. So that's going to be negative 0.67, so it's 6.66666 repeating. And then if we multiply that by 2, we will get the change for ammonia, which is positive 1.33. So we take the change for hydrogen, divide it by 3 to get the change for nitrogen. We can then take the change for nitrogen, multiply it by 2 to get the change for ammonia. So our equilibrium concentrations will be 2 minus 0.67, so 1.33 for nitrogen, our final concentration, 0 for hydrogen, and 1.33 for ammonia. This is our maximum theoretical yield. So that's what we will be comparing our equilibrium concentration with. For our equilibrium concentration, we're going to keep just practicing our ACE tables. So you could skip this step and still get the question right because you are looking at the equilibrium concentration which you're given. Sometimes you won't be. Sometimes you'll have to actually solve for it using the X method. So we start with 2 for each of these and 0 for ammonia. At equilibrium, ammonia is 0.25, meaning it had a change of positive 0.25. If we divide that by 2, the change for nitrogen is negative 0.125, giving us an equilibrium concentration of 1.875. And the change for hydrogen will be negative 0.375, which gives us an equilibrium concentration of 1.625. So we can see that we have quite a bit of reactant left, not a lot of product compared to our theoretical or our quantitative reaction. So we're now going to calculate our percent yield. So our percent yield is going to have the concentration of ammonia at equilibrium divided by the concentration of ammonia from our quantitative reaction times 100. So we have 0.25 moles per liter at equilibrium, and our theoretical would be 1.33 moles per liter. And so 0.25 divided by 1.33, and then we multiply that by 100%, we get a yield of 19%. A low yield like this indicates this is a reactant-favored reaction.